probability. Introduction. In this chapter, we shall discuss the important concept of conditional probability of an event, given that another event has occurred, which will be helpful in understanding the Bayes' theorem, multiplication rule of probability, and independence of events. We shall also learn an important concept of random variable and its probability distribution, and also the mean and variance of a probability distribution. In the last section of the chapter, we shall study an important discrete probability distribution called binomial distribution. Throughout this chapter, we shall take up the experiments having equally likely outcomes, unless stated otherwise. Conditional probability. If we have two events from the same sample space, does the information about the occurrence of one of the events affect the probability of the other event? Let us try to answer this question by taking up a random experiment in which outcomes are equally likely to occur.
If E and F are two events associated with the sample space of a random experiment, the conditional probability of the event E given that F has occurred, that is, P of E by F is given by P of E by F is equal to P of E intersection F by P of F, provided that P of F is not equal to 0. Consider the experiment of tossing 3 fair coins. The sample space of the experiment is S is equal to H, 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 T, H, T, H, T, H, 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 T, 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 H, T, 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 H, T, 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 where H represents the head and T represents tail. Since the coins are fair, we can assign the probability 1 by 8 to each sample point. Let E be the event at least 2 heads appear, and F be the event first coin shows tail. Then E is equal to H, 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 T, H, T, H, T, H, H, and F is equal to T, H, H, T, H, T, 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 H, T, T, T. Therefore, P of E is equal to P of H, H, H plus P of H, H, T plus P of H, T, H plus P of T, H, H is equal to 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8 is equal to 1 by 2, and P of F is equal to P of T, H, H plus P of T, H, T plus P of T, T, H plus P of T, T, T is equal to 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8 is equal to 1 by 2. Also, E intersection R is equal to T, H, H with P of E intersection F is equal to P of T, H, H is equal to 1 by 8.
Probability. Conditional probability. Now, suppose we are given that the first coin shows tail, that is, F occurs, then what is the probability of occurrence of E? With the information of occurrence of F, we are sure that the cases in which first coin does not result into a tail should not be considered while finding the probability of E. This information reduces our sample space from the set S to its subject F for the event E. In other words, the additional information really amounts to telling us that the situation may be considered as being that of a new random experiment for which the sample space consists of all those outcomes only now. The sample point of f, which is favorable to the occurrence of the event f. Now, the sample point of f, which is favorable to event e, is THH. Thus, probability of e, considering f as the sample space equal to 1 by 4, or probability of e is given that the event f has occurred equal to 1 by 4. This probability of the event e is called the conditional probability of e given that f has already occurred and is denoted by p e by f. Thus, p of e by f equal to 1 by 4. Note that the elements of f which favor the event e are the common elements of e and r, that is, the sample points of e intersection f. Thus, we can also write the conditional probability of e given that f has occurred as p of e by f equal to number of elementary events favorable to e intersection f by number of elementary events which are favorable to f equal to n of e intersection f by n of f. Dividing the numerator and the denominator by total number of elementary events of the sample space, we see that p of e by f can also be written as n of e intersection f by n of s by n of f by n of s equal to p of e intersection f by p of f, equation 1.
Properties of conditional probability. Let E and be events of a sample space S of an experiment. Then we have property 1. P of S by F is equal to P of F by F is equal to 1. We know that P of S by F is equal to P of S intersection F by P of F is equal to P of F by P of F is equal to 1. Also, P of F by F is equal to P of F intersection F by P of F is equal to P of F by P of F is equal to 1. Thus, P of S by F is equal to P of F by F is equal to 1. Property 2. The proof is shown on the screen. Property 3. The proof is shown on the screen. Example. A family has 2 children. What is the probability that both the children are boys given that at least of them is a boy?
Example, 10 cards numbered 1 to 10 are placed in a box, mixed up thoroughly, and then one card is drawn randomly. If it is known that the number of the drawn card is more than 3, what is the probability that it is an even number? Solution. Let A be the event, the number on the card drawn is even, and B be the event, the number on the card drawn is greater than 3. We have to find P of A by B. Now, the simple space of the experiment is S equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then A equal to 2, 4, 6, 8, 10. B equal to 4, 5, 6, 7, 8, 9, 10. And A intersection B equal to 4, 6, 8, 10. Also, P of A equal to 5 by 10, P of B equal to 7 by 10, and P of A intersection B equal to 4 by 10. Then P of A by B equal to P of A intersection B by P of B equal to 4 by 10 by 7 by 10 equal to 4 by 7.
Multiplication theorem. Let E and F be two events associated with a sample space S. Clearly, the set E intersection F denotes the event that both E and F have occurred. In other words, E intersection F denotes the simultaneous occurrence of the events E and F. The event E intersection F is also written as EF. Very often, we need to find the probability of the event EF. For example, in the experiment of drawing two cards one after the other, we may be interested in finding the probability of the event a king and a queen. The probability of event EF is obtained by using the conditional probability as obtained below.
Multiplication theorem on probability. We know that the conditional probability of the event E given that F has occurred is denoted by P of E by F and is given by P of E by F equal to P of E intersection F by P of F, comma, P of F is not equal to 0. From this result, we can write P of E intersection F equal to P of E into P of E by F, equation 1. Also, we know that P of E by F equal to P of F intersection E by P of E, comma, P of E is not equal to 0. Or P of F by E equal to P of E intersection F by P of E, since E intersection F equal to F intersection E. Thus, P of E intersection F equal to P of E into P of F by E, equation 2. Combining 1 and 2, we find that P of E intersection F equal to P of E, P of F by E, equal to P of F into P of E by F, provided P of E is not equal to 0 and P of F is not equal to 0. The above result is known as multiplication rule of probability.
Example: an urn contains 10 black and 5 white balls. 2 balls are drawn from the urn one after the other without replacement. What is the probability that both drawn balls are black? Independent events. Consider the experiment of drawing a card from a deck of 52 playing cards, in which the elementary events are assumed to be equally likely. If E and F denote the events, the card drawn is a spade and the card drawn is an ass respectively, then P of E is equal to 13 by 52 is equal to 1 by 4 and P of S is equal to 4 by 52 is equal to 1 by 13. Also, E and F is the event the card drawn is the ass of spades, so that P of E intersection F is equal to 1 by 52. Hence, P of E by F is equal to P of E intersection F by P of F is equal to 1 by 52 by 1 by 13 is equal to 1 by 4. Since P of E is equal to 1 by 4 is equal to P of E by F, we can say that the occurrence of event F has not affected the probability of occurrence of the event E. We also have P of F by E is equal to P of E intersection F by P of E is equal to 1 by 52 by 1 by 4 is equal to 1 by 13 is equal to P of F. Again, P of F is equal to 1 by 13 is equal to P of F by E, shows that the occurrence of event E has not affected the probability of occurrence of the event F. Thus, E and F are two events such that the probability of occurrence of one of them is not affected by the occurrence of the other. Such events are called independent events. Example: an unbiased die is thrown twice. Let the event A be odd number on the first throw and B the event odd number on the second throw. Check the independence of the events A and B.
Example: if A and B are two independent events, then the probability of occurrence of at least one of A and B is given by 1 minus P of A dash and P of B dash. Solution: we have P at least one of A and B equal to P of A union B equal to P of A plus P of B minus P of A intersection B equal to P of A plus P of B minus P of A into P of B equal to P of A plus P of B 1 minus P of A equal to P of A plus P of B into P of A dash equal to 1 minus P of A dash plus P of B into P of A dash equal to 1 minus P of A dash 1 minus P of B equal to 1 minus P of A dash into P of B dash.
Bayes theorem. Consider that there are two bags 1 and 2. Bag 1 contains 2 white and 3 red balls and bag 2 contains 4 white and 5 red balls. One ball is drawn at random from one of the bags. We can find the probability of selecting any of the bags, that is 1 by 2, or probability of drawing a ball of a particular color, say white, from a particular bag, say bag 1. In other words, we can find the probability that the ball drawn is of a particular color if we are given the bag from which the ball drawn. But can we find the probability that the ball drawn is from a particular bag, say bag 2, if the color of the ball drawn is given? Here we have to find the reverse probability of bag 2 to be selected when an event occurred after it is known. Famous mathematician John Bayes solved the problem of finding reverse probability by using conditional probability. The formula developed by him is known as Bayes theorem. Partition of a sample space. A set of events E1, E2 up to En is said to represent a partition of the sample space S as follows. In other words, the events E1, E2 up to En represent a partition of the sample space S if they are pairwise disjoint, exhaustive, and have non-zero probabilities. As an example, we see that any non-empty event E and its complement E dash form a partition of the sample space S since they satisfy E intersection E dash is equal to pi and E union E dash is equal to S. From the Venn diagram, one can easily observe that if E and F are any two events associated with a sample space S, then the set E intersection F dash, E intersection F, E dash intersection F, E dash intersection F dash is a partition of the sample space S. It may be mentioned that the partition of a sample space is not unique. There can be several partitions of the same sample space. We shall now prove a theorem known as theorem of total probability. Theorem of total probability. Let E1, E2 up to En be a partition of the sample space S, and suppose that each of the events E1, E2 up to En has non-zero probability of occurrence. Let A be any event associated with S. Then the theorem is given as follows. The proof is given on the screen.
Bayes' theorem. If E1, E2 up to En are n non-empty events which constitute a partition of sample space S, that is E1, E2 up to En are pairwise disjoint, and E1 union E2 union up to union En is equal to S, and A is any event of non-zero probability, then the theorem is stated as follows and the proof is also given.
Example. Given three identical boxes 1, 2 and 3, each containing 2 coins. In box 1, both coins are gold coins. In box 2, both are silver coins. And in box 3, there is 1 gold and 1 silver coin. A person chooses a box at random and takes out a coin. If the coin is of gold, what is the probability that the other coin in the box is also of gold? Random variables and its probability distributions. We have learnt about random experiments and formation of sample spaces. In most of these experiments, we were not only interested in the particular outcome that occurs, but rather in some number associated with that outcomes as shown in the following examples or experiments.
Random variables and its probability distributions. Definition 4. A random variable is a real valued function whose domain is the sample space of a random experiment. For example, let us consider the experiment of tossing a coin 2 times in a succession. The sample space of the experiment is S equal to HH, HT, TH, TT. If X denotes the number of heads obtained, then X is a random variable, and for each outcome, its value is as given below. X of HH equal to 2, X of HT equal to 1, X of TH equal to 1, X of TT equal to 0. More than one random variables can be defined on the same sample space. For example, let Y denote the number of heads minus the number of tails for each outcome of the above sample space S. Then Y of HH equal to 2, Y of HT equal to 0, Y of TH equal to 0, and Y of TT equal to minus 2. Thus, X and Y are two different random variables defined on the same sample space S.
Example. A bag contains 2 white and 1 red balls. One ball is drawn at random and then put back in the box after noting its color. The process is repeated again. If X denotes the number of red balls recorded in the 2 draws, describe X. Probability distribution of a random variable. Let us look at the experiment of selecting one family out of 10 families F1, F2 up to F10 in such a manner that each family is equally likely to be selected. Let the families F1, F2 up to F10 have 3, 4, 3, 2, 5, 4, 3, 6, 4 and 5 members respectively. Let us select a family and note down the number of members in the family denoting X. Clearly, X is a random variable defined as stated further.
Probability distribution of a random variable. Now, X will take the value 2 when the family F4 is selected. X can take the value 3 when any one of the families F1, F3, F7 is selected. Similarly, x equal to 4 when family F2, F6 or F9 is selected, x equal to 5 when family F5 or F10 is selected, and x equal to 6 when family F8 is selected. Since we had assumed that each family is equally likely to be selected, the probability that family F4 is selected is 1 by 10. Thus, the probability that x can take the value 2 is 1 by 10. We write P of x equal to 2 equal to 1 by 10. Also, the probability that any one of the families F1, F3 or F7 is selected is P of F1, F3, F7 equal to 3 by 10. Thus, the probability that x can take the value 3 equal to 3 by 10. We write P of x equal to 3 equal to 3 by 10. Similarly, we obtain P of x equal to 4 equal to P of F2, F6, F9 equal to 3 by 10, P of x equal to 5 equal to P of F5, F10 equal to 2 by 10 and P of x equal to 6 equal to P of F8 equal to 1 by 10. Such a description, giving the values of random variable along with the corresponding probabilities, is called the probability distribution of the random variable x.
Definition: the probability distribution of a random variable x is the system of numbers as given below. The real numbers x1, x2 up to xn are the possible values of the random variable x, and pi I is equal to 1, 2 up to n is the probability of the random variable x taking the value xi, that is, p into x is equal to xi is equal to pi dot.
Example. Find the probability distribution of a number of doublets in 3 throws of a pair of dice. Mean of a random variable. In many problems, it is desirable to describe some feature of the random variable by means of a single number that can be computed from its probability distribution. Few such members are mean, median, and mode. In this section, we shall discuss mean only. Mean is the measure of location or central tendency in the sense that it roughly locates a middle or average value of the random variable.
Mean of a random variable. Let x be a random variable whose possible values x1, x2, x3 till xn occur with probabilities p1, p2, p3 till pn respectively. The mean of x, denoted by nu, is the number. Sigma n I equal to 1 xi pi, that is, the mean of x is the weighted average of the possible values x, each value being weighted by its probability with which it occurs. The mean of a random variable x is also called the expectation of x, denoted by E of x. Thus, E of x equal to nu equal to sigma n I equal to 1 xi pi equal to x1 p1 plus x2 p2 plus till xn pn. In other words, the mean or expectation of a random variable x is the sum of the products of all possible values of x by their respective probabilities.
Example. Let a pair of dice thrown and the random variable x be the sum of the numbers that appear on the two dice. Find the mean or expectation of x. Variance of a random variable. The mean of a random variable does not give us information about the variability in the values of the random variable. In fact, if the variance is small, then the values of random variable are close to the mean. Also, random variables with different probability distributions can have equal means as shown in the following distributions of x and y.
Variance of a random variable. The variables x and y are different. However, their means are same. It is also easily observable from the diagrammatic representations of these distributions. To distinguish x from y, we require a measure of the extent to which the value of the random variable spread out. In statistics, we have studied that the variance is measure of the spread or scatter in data. Likewise, the variability or spread in the values of a random variable may be measured by variance.
Example: two cards are drawn simultaneously or successively without replacement from a well-shuffled pack of 52 cards. Find the mean, variance, and standard deviation of the number of kings.
Bernoulli trials and binomial distribution. Many experiments are dichotomous in nature. For example, a tossed coin shows a head or tail. A manufactured item can be defective or non-defective. The response to a question might be yes or no. An egg has hatched or non-hatched. The decision is yes or no, etc. In such cases, it is customary to call one of the outcomes a success and the other not success or failure. For example, in tossing a coin, if the occurrence of the head is considered a success, then occurrence of tail is a failure.
Bernoulli trials and binomial distribution. Definition 8. Trials of a random experiment are called Bernoulli's trials if they satisfy the following conditions. 1. There should be a finite number of trials. 2. The trials should be independent. 3. Each trial has exactly two outcomes, success or failure. 4. The probability of success remains the same in each trial. For example, throwing a die 50 times in a case of 50 Bernoulli's trials, in which each trial result in success, say an even number, or failure, an odd number, and the probability of the success, P, is same for all 50 throws. Obviously, the successive throws of the die are independent experiments. If the die is fair and have 6 numbers, 1 to 6, written on 6 faces, then P equal to 1 by 2 and Q equal to 1 minus P equal to 1 by 2 equal to probability of failure.
Example: 6 balls are drawn successively from an urn containing 7 red and 9 black balls. Tell whether or not the trials of drawing balls are Bernoulli trials when, after each draw, the ball drawn is subdivision 1 replaced, subdivision 2 not replaced in the urn.
binomial distribution. Consider the experiment of tossing a coin in which each trial results in success, say heads, or failure, tails. Let S and F denote respectively success and failure in each trial. Suppose we are interested in finding the ways in which we have one success in 6 trials. Clearly, 6 different cases are there as listed below.
Example. If a fair coin is tossed 10 times, find the probability of subdivision 1 exactly 6 heads, subdivision 2 at least 6 heads, subdivision 3 at most 6 heads. Example. A and B throw a die alternatively till one of them gets a 6 and wins the game. Find their respective probabilities of winning if A starts first.